Welcome back to Physics 142 Online. Today we're going to look at the properties of lenses in a particular approximation that we call the thin lens approximation. First, let's just look at what happens when light from an object passes from air into a lens, which here has index of refraction n2 greater than n1. And what we find, without worrying too much about the specific details of this diagram, is that the light from a particular point on the object travels lots of different paths when it passes into the lens, but that from that one point, all of the paths will intersect at a certain point on the other side of the lens that's called the image point. And so we define an object, which we usually use an upright arrow to indicate, and then an image, which is another arrow. It could be larger, it could be smaller, depending on what the focal length of the lens is and where the object is located. So rather than deal with the specific details of what happens when the paths of light hit that curved surface of the lens and either bend or in some cases pass straight through, we're going to use an approximation where we think of the lens as just being at a specific plane, where there's a plane that passes right through the center of the lens. So a lens in general is a piece of refracting material with two curved surfaces. And so the light rays are generally bent separately at the two surfaces, but if these two curved surfaces form a thin lens, then we can construct the approximate location of the image from just the object position and a knowledge of the focal length of the lens. So here are the two general types of lenses: a converging lens, where it's thicker at the center than at the edges, and a diverging lens, where it's thinner at the center than it is at the edges. And these are also called convex and concave lenses. You can have various types of these where one surface is curved and the other is flat, but we'll focus our attention, no pun intended, just on these two types of lenses. And here is how we understand the way that light behaves when it passes from air into a lens material. We can do this experimentally, as I will show in class, where we have light that comes in parallel to the optical axis, and the optical axis is the horizontal line that's perpendicular to the plane of the lens. So light that comes in parallel to that direction, when it interacts with the lens, it's bent toward a specific point on the other side of the lens called a focal point. And this, by the way, happens for a converging lens. For a diverging lens, we'll show that it's just a little bit different. The situation is a little bit different. And then, secondly, we can also show that a ray passing through the center of the lens, through the exact center, it's bent once on the front surface and then again on the back surface, and it's easy enough to prove that the path that it has at the very end is parallel to the incident path, as long as the lens is thin. And if the lens is really thin, then there's really not very much of a shift at all as a result of these two refraction events. So we will take the approximation that this ray passes through the center of the lens and emerges undeflected. And those two observations that we can make using beams of light and a lens, a very thin one, give us three principal rays for a converging lens. First, the top ray is the parallel ray. It comes in parallel to the optical axis, hits the lens, and we're going to draw it as if it hits the plane at the center of the lens, and it's bent through the focal point on the other side. Then there's the central ray that passes from a certain point on the object through the center of the lens and goes through undeflected. So that's just a straight line path. And then the third ray, what's called the focal ray, is really the inverse of the first one. So if light were to come in horizontal from the right side and pass through the lens, it would be bent through the focal point to get to this point on the object. So we know that in reverse, light from that point on the object, if it passes through the focal point and hits the lens, it will then emerge parallel to the optical axis. And if this sketch is drawn carefully, and we can verify this using some nice light sources, these three rays will all intersect at a certain point that is going to be the corresponding point that we started from, let's say the tip of the object, and it will form the tip of the image. And you can see in this case that while that point originally was above the central axis, the optical axis, now in the image it's below. And as a result, the image is inverted. So these are called the three principal rays, and we're going to use their properties in the next slide to deduce a quantitative relationship that tells us where the image is located in terms of where the object is and the focal distance. So this distance s tells us how far the object is from the lens. S prime is the image distance, and then small lowercase f represents the focal length from the focus to the center of the lens. All right, so here's the diagram, and we're going to be looking at the right triangles that contain these angles alpha and theta to determine the appropriate quantitative relationships for thin lenses. First of all, if we look at the right triangle that has theta as the angle, tangent of theta will be the opposite side, the y value, divided by s, which is the base of that right triangle. On the other side of the lens, tan theta, since it's that same angle theta, the central ray, remember, goes through undeflected, so those angles are the same. So tan theta over here is the distance y prime divided by s prime. Only since the image is inverted, the y prime distance in this case is considered negative. So we have to put a minus sign into that equation. So we've got two different expressions for tan of theta. This allows us to get a result for the magnification, because it's quite simple to see that the magnification should be defined as the image height divided by the object height. That way, if one of them is greater than the other one, you may have an image that's enlarged. On the other hand, if the relationship is the reverse, you may have an image that's reduced in size. So here, if we just solve for that ratio y prime over y, from our original equation, we can see that it's equal to minus s prime over s, and that's the magnification equation. We can go further by considering, oh, that's right, there is a sign convention here. Of course, you can see that if y prime is negative, then that means that the object is inverted, and that will give a negative value for m. The image is inverted. If y prime is positive, then you'll have two positive values that make up that quotient, and m will be positive, and that will represent an upright image. And that's not the case in the sketch shown here, but we can do examples where that could be the case in class. So now let's focus our attention on the other right triangle that has alpha as its angle. There's also two of those. So the tangent of alpha on the left-hand side, tan alpha, would be the height y of the object divided by this distance here, which goes from the object to the focal point. And if you look at that, that's s, the object distance, minus f, the focal distance, the focal length. So that's one expression. And then we can also look at the tangent of alpha on the right-hand side of the focal point and see that the opposite side is the image height, y prime, and then we have to divide by the focal length. And we put a minus sign in there again because in this case y prime has a negative value, and we want the tangent of alpha to be a positive value. So those are equal to each other as well. So now what we'll do is take the magnification equation and the relationship here between y prime and s prime and substitute that into this equation that came from the tangent of alpha. And I'm going to skip the steps, but when we do that, you'll be able to see that you'll eliminate the quantities y and y prime, and you'll end up with an equation that just relates s, f, and s prime. And so we can rewrite this equation in a little bit more elegant form as a relationship between the reciprocals of these distances. So if we solve this equation for 1 over f, we find that 1 over f is 1 over s plus 1 over s prime. The reciprocal of the object distance plus the reciprocal of the image distance gives the reciprocal of the focal length. And this is called the thin lens equation. This is going to be the quantitative relationship that we will use if we're given an object position and a focal length and a lens position. Then we can figure out where the image is located. We can also find out is the image enlarged or is it reduced in size, and then is it upright or is it inverted. So a couple of sign conventions. I've already mentioned one of those, that when m is greater than 0, the image is upright. When m is less than 0, the image is inverted. But there's also some other ones. For a converging lens, the focal length in this equation is positive. For this equation to hold true for a diverging lens, the focal length, whatever the numerical value is, it's considered to be negative. So we still use the same equation as long as we keep track of the signs that way. Similarly, if the image or the object are real, which means they actually are at a point in space where the light rays actually cross, then S and S prime in this equation are positive. So S and S prime are greater than 0 for real objects and images. S and S prime are less than 0 for virtual objects and images. And a virtual image is a point where it just looks like the rays of light cross. They actually don't cross at a particular point in space physically, but when we look through a lens at a particular object, it looks like the image is at a certain position. So we'll show examples of that in class as well. And finally, the magnitude of M, although M could be positive or negative, if the magnitude is greater than 1, you have an enlarged image. If it's less than 1, you have a reduced image. So those things just have to be kept in mind when solving problems using the thin lens equation. Finally, here's an example. Okay, an object is 24 centimeters away from a double convex lens with a focal length of 12 centimeters. I didn't draw the sketch with the focal point in here, but in this sketch it would be halfway between the center of the lens and the object, which we indicate as an upright arrow. So we're going to use the thin lens equation to find the location of the image and to find its magnification, and based on those results we will be able to tell whether the image is real or virtual, upright or inverted, and then enlarged or reduced. So we apply the thin lens equation. We start with that. What are we trying to solve for? We're trying to solve for the image location. So we're trying to solve for S prime. So when we solve for S prime, it's 1 over S prime is negative 1 over S plus 1 over F. Now we can plug in the numbers here and keep track of the signs. There's a minus sign here. S is 24. That's a positive value because we have a real image. The light actually is coming, sorry, a real object. The light actually is coming from the object to pass through the lens. The focal length is positive because it's a converging lens, and when we simplify, we get 1 over 24 centimeters. So 1 over S prime is 1 over 24 centimeters. That means S prime is equal to 24 centimeters, and now we can answer, we can find the magnification. But first of all, we know that that's a real image, because if S prime is positive, it's a real image. And what that means is the image is on the right-hand side of the lens. The light coming from the object passes through the lens and gets bent, and those light rays will intersect over on the right-hand side. So that's a real image. Solving for the magnification, minus S prime over S, minus 24 over 24, so we get negative 1. And right away we can say it's negative, so that means the image is inverted, and the size of the image is the same as the size of the object because the magnitude is just equal to 1. So if we were to draw the ray diagram, and we'll get some practice doing that in class, we would find that the image would be inverted, it would be below the optical axis on the right-hand side, and it would be the same distance away from the lens as the object is. So we'll have lots of practice doing these kinds of questions and problems in class and on your homework assignment. I will see you in class.